Good morning. It's online lesson 8, physics 11, and we're going to talk about the law of conservation of momentum today. Collisions and explosions are quite a big part of momentum. So here we go. We talked about momentum before in lesson 7, but just as a reminder, P is the symbol for momentum, not capital P, but a little p. And we're not really sure where it comes from. Capital P is power, but little p stands for momentum. And momentum is mass times velocity. And it's a vector, so direction's important. So whether it's north, east, south, west, left, right, that kind of thing. And the units are mass is in kilograms, and velocity is meters per second. So momentum has units of what we call kilogram meters per second. One of the laws of physics is the law of conservation of momentum. You've already come across a law of conservation of mass in chemistry. Initial total mass is equal to initial total mass is equal to final total mass. It's the same thing here with momentum. Initial total momentum of any objects in a collision is equal to the final total momentum of those objects. So the law of conservation of momentum says that, for instance, if there are two objects, that the total initial momentum of those two objects before a collision or explosion or some sort of interaction will equal the final total momentum. And just to clarify, if there's one object, we'll call it M1, its initial momentum would be P1 initial. So momentum of the first one initially, and it has a final momentum. So M1 has a final momentum of P1 final. So those are the symbols that we'll use. If we had two objects, we'll call one M1 and the other one M2, and they were involved in a collision or explosion. The initial total momentum equals the final total momentum, and in terms of an equation it would look like this. P1 initial plus P2 initial equals P1 final plus P2 final. And if we expanded that out a little bit, momentum being mass times velocity, we get M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And that's a usable form of the equation. Some textbooks, they might say, instead of initial total momentum, they'll say net initial momentum. So net meaning total initial momentum equals net final momentum. It's the same thing. This is just for two objects. You have to remember too that these are vectors, so you need to consider direction. So as we talked about before, if you have north, east, south, and west, just like a number line, this part going up is positive, going east is positive, south is negative, west is negative. And by the same token, up, down, up would be positive, down would be negative, like it was for gravity. And right is positive, and left is negative. This online lesson 8 right here features 3 example problems that we'll do. One with a fish eating another fish, two with 2 bumper boats colliding. And then the third one is in space where the astronaut has 0 friction and no weight. And this object has no weight too. They both have mass, but this one has no friction too. And the astronaut's actually pushing this bag towards us. So example question number 1 is about a 5 kilogram fish swimming to the right at 1 meter per second, and it swallows a 1 kilogram fish swimming to the left. And the question is, at what velocity must that smaller fish have been swimming to bring the bigger fish to 0 meters per second from 1 meter per second after its lunch? So it slowed that fish, the big one, right down to 0. And both of them aren't moving after the collision. And in a diagram, we've got one fish, M1, traveling to the right at 1 meter per second. This guy here is 5 kilograms. And this fish here is 1 kilogram. And we don't know what its speed is. All we know is that the momentum after is 0. So brings both of them to a stop. So initially, that's the situation we have. And finally, we have no momentum. Like they're both stopped. There's no velocity. So let's use the equation and find the answer. In mathematical form, this is the law of conservation of momentum for two things that are colliding. In this case, two fish. So we've got initial momentum of the first fish plus initial momentum of the second fish equals initial momentum, or final momentum, I should say, of the first fish and the final momentum of the second fish. And when you expand it out, the bigger equation looks like this. We can actually put in numbers now. The first fish had a mass of 5 kilograms and a speed of 1 meter per second. The other fish had a mass of 1 kilogram. We don't know what its initial speed is, though. What we do know, though, is that the speed of both fish at the end were 0. In fact, M1 ate M2. So M2 is inside of M1. They're combined. So mathematically, combined mass, and they share the same final speed too, because M1 has eaten M2. They're together. So they have the same final speed. So if I know that final speed is 0, I have M1 plus M2 times 0. That whole side is 0. If you multiply anything by 0, the entire side is 0. On this side I've got 5 times 1, so 5 kilogram meters per second, plus 1 kilogram times V2F. V2 initial, I should say. And just to do the algebra, I want variables on one side, so in this case the V2 initial is on this side, and then the numbers on the other side. So as you guys would do in math, 1 kilogram times V2y. I just have that all on one side. Bring this to the other side, so I have to subtract this from this side, do the same thing over here. So what I do to one side, I have to do to the other. So I've got minus 5 kilogram meters per second. That is the unit for momentum, kilograms times meters per second. And then just to finish up the math, I want to divide this entire side by the 1 kilogram. I just want V2 initial, what the speed of the fish was in the first place. So divide this whole side by 1 kilogram, and then divide this side by 1 kilogram. And of course the kilograms cancel, and I'm just left with minus 5 divided by 1 in meters per second. So minus 5 meters per second. So that was the speed that fish 2, the one that was traveling in this direction, the smaller fish, was traveling. So the minus means going that way, which you could say is to the west or to the left. at 5 meters per second. So you could say 5 meters per second to the west. Or you could have said 5 meters per second to the left. But that's what that negative sign means. Question number 2, it is about bumper boats. Giving you a bit of data, blue boat in this picture, for example, number 2, is traveling to the right at 1.5 meters per second. The red boat is traveling to the left at 1.77 meters per second. Here's the question. If after the collision, boat 1, the blue boat, is traveling backwards now at 1.25 meters per second, then what is the final speed of the red boat? In mathematical form and substituting all the numbers in, we get, without the units, because it gets a little confusing putting the kilograms and meters per second and so on in there. As long as that is in kilograms and that's in meters per second, we'll have proper units for what our final answer will be. So 101 in kilograms times 1.50 in meters per second, plus the red boat's 112 times, you have to put the negative sign in because it was originally going 1.77 meters per second that way, is equal to 101 times now after the collision it's going backwards, plus 112 times its V2F. Doing some calculations, this is what it looks like now. And we want to have just variables on one side and then numbers on the other side. So here we do the algebra according to BEDMAS. Next step, bringing the numbers over, I've got 151.5, true, minus 198.24. When I bring this negative over, it's a negative negative, that will be a positive. And the only thing I have left on this side is that. And final step, it's just taking 79.51 dividing by 112. So do that to both sides. That side divide by 112, this side divide by 112. And 79.51 divided by 112 is 0.710 meters per second. So this fish, the M2, is actually going to the east now, the positive direction, at 0.710 meters per second. In this example, we have an astronaut pushing the bag towards us. We'll say towards us is to the south. And as he pushes it, he's not moving. But after he pushes it, he does start to move. So Newton's third law, for every push there's an equal and opposite push. When he pushes on the bag towards us, which is to the south, he'll end up going to the north. And we've got the equation for the law of conservation of momentum here, and I'll just put in the numbers for the astronaut and for the luggage. Initially, they are not moving. The numbers. So they're initially not moving, so there's no initial momentum. So the total initial momentum is 0. And the next step, I want to get this number onto this side and have just the variables here. When I moved it, now divide both sides by 75.2. Looks like that. The answer turns out to be 0.755 meters per second to the north.